In this video, we'll learn about simple harmonic motion graphs. We'll discuss displacement time, velocity time, acceleration time, and acceleration displacement graphs. Let's begin with displacement time graphs. In the previous video, we analyzed simple harmonic motion through the oscillations of a horizontal spring. We began with an uncompressed spring, which then we compressed and released, observing its motion through one full cycle or oscillation. When the compressed spring is released, the object attached to it moves to the right. After passing through the equilibrium position, the spring reaches maximum extension, and then the object moves back to the left through the equilibrium position until it is fully compressed again. We use the simple scale to show the equilibrium position, the negative direction, and the positive direction. Afterwards, we created a table to describe x the displacement, v the velocity, f the force, and a the acceleration at these 5 different positions during an oscillation. The word max shows that the magnitude of the given quantity at the given position is at its maximum. 0 logically shows that the quantity is 0, and the positive and negative signs indicate the direction of the given quantity. For more details about how we got this table, feel free to watch the previous video named Simple Harmonic Motion. Let's see how the displacement time graph looks like for this situation. Uppercase T on the horizontal axis shows the time period of the oscillation. In other words, the time it takes for the object to complete one full cycle. The points labeled as x max show the 2 maximum displacement positions of the object, so when the spring is fully compressed and fully stretched. 0 denotes the equilibrium position. Let's plot how x, the displacement, varies with time. At the start, when the spring is fully compressed, time is 0, and displacement is at its maximum negative value. This moment can be represented by this point on the graph. In the second position, when the object is moving to the right and passing through its equilibrium position, it has completed a quarter of a full oscillation. So the time at this point is a quarter of the time period, or t over 4. Displacement here is 0. After another quarter of a full oscillation, so at t over 2, the spring is fully stretched and the object is at its maximum displacement position, but this time in the positive direction. At 3/4 t, or 3t over 4, the object is again passing through the equilibrium position, so its displacement is 0. Finally, after one full oscillation, at time t, the object is back to its starting position when the spring is fully compressed, and displacement is at its negative maximum. Let's connect these dots to complete the displacement time graph. It's important to note that our displacement time graph starts at the negative maximum displacement position because this is where we started observing the motion of the object. If we would have started our timer when the object is passing through its equilibrium position or when it is at its positive maximum displacement position, the graph would be shifted to the left or to the right. Let's move on to velocity time graphs. Here we also have time on the horizontal axis, uppercase T representing the time taken by the mass to complete one full oscillation. Velocity is represented on the vertical axis, where Vmax represents the point where the magnitude of the mass's velocity is maximum. Let's start plotting the graph. Looking at the second column in our table, we can see that in the first position, when the spring is fully compressed, velocity is 0. In the second position, at t over 4, velocity is at its maximum positive value, so here. At t over 2, when the spring is fully extended and the object is all the way to the right, velocity again is 0. Then at the fourth position, at 3t over 4, the object is again at the equilibrium position, this time moving to the left. Looking at the second column of the table, we can see that velocity is at its maximum negative value, so here. Finally, after a full oscillation at t, the spring is fully compressed, the object stops for a moment, so velocity is 0. Here is the velocity time graph that we get when we connect these points. Just as for the displacement time graph, the velocity time graph could be shifted to the left or to the right, depending on when we start observing the motion of the object. By now you have probably realized that the shape of the displacement time graph and the velocity time graph is similar. A major difference is that these graphs are shifted horizontally when compared to each other. In physics, we say that the graphs have a phase difference. You might have also guessed that the acceleration time graph will also have a similar shape and will have a phase difference compared to the other two graphs. We'll explore phase difference in more detail in the next video. Now, let's move on to the acceleration time graph. Based on our experience with the previous two graphs, we can now quickly plot the acceleration time graph using the final column of our table. At t equals 0, acceleration is at its maximum positive value. At t over 4, it is 0. At t over 2, it is at its maximum negative value. At 3t over 4, it is 0 again. And at t, it is back at its maximum positive value. Connecting the points, we get this graph. Let's move on to the acceleration displacement graph. Our grid looks a bit different here, but xmax and amax still represent the maximum displacement and maximum acceleration values. Let's use the first and the last columns of the table to plot this graph. In the first row of the table, when the spring is fully compressed, x, the displacement, is at its maximum negative value, while a, the acceleration, is at its maximum positive value. We can represent this moment by the following point. In the second row of the table, both displacement and acceleration are 0. This is the point we get. When the spring is fully extended, displacement is at its maximum positive, while acceleration is at its maximum negative value, giving us this point. The fourth row again gives us the point at the origin, where both quantities are 0, and the last row gives us the point that we plotted all the way to the left, where displacement is at its maximum negative and acceleration is at its maximum positive value. Connecting the points, we get a straight line. In the previous video, we saw that the equation connecting the acceleration and the displacement is a equals to negative kx, where k is a constant. Considering this equation, the graph we got makes sense because it is a straight line with a negative gradient passing through the origin. Let's summarize what we have learned in this video. We discussed the 4 simple harmonic motion graphs that are part of the IB Physics syllabus. These are displacement time, velocity time, acceleration time, and acceleration displacement. We mentioned that the shape of the first 3 graphs is similar, and that there is a phase difference between these graphs that we'll explore in the next video. For the acceleration displacement graph, we recall the equation a is equal to negative kx from the previous video, and discussed how this equation matches up well with the graph, since we have a straight line with a negative gradient that passes through the origin. This completes our discussion of simple harmonic motion graphs.